Hello, I'm here to present our work RP-VIO, Robust Plane-Based Visual-Inertial Odometry for Dynamic Environments. My name is Karnik Ram. I'm a master's student in the Robotics Research Center at IIIT Hyderabad. This is work done along with my colleagues Chaitanya Sudarshan and Professor Madhav Krishna. Visual-Inertial Odometry algorithms have emerged as a cheap and compact solution for accurate localization. They are increasingly being used for many AR/VR applications and mobile robot navigation. Yet, these algorithms continue to struggle in dynamic environments. In scenes with multiple independently moving dynamic objects, such as the ones shown here, a simple ransack-based approach to filter out the dynamic outliers tends to fail, leading to significant errors or complete tracking failure. A common approach to deal with this problem is to use semantic segmentation models to mask out regions belonging to potentially dynamic classes such as people or vehicles. A problem with this approach is that it is difficult to segment out all possible dynamic objects, as this list is often not finite and tends to vary across scenes. For example, in this image shown here, though it is possible to segment out the people, it is not trivial to train for or segment the other dynamic objects such as trolleys, bags, and paper hangers. We believe a better approach is to directly segment the static regions in a scene, which in most man-made environments appear in the form of large planar surfaces such as the floor. These planes also offer additional geometric constraints which can be used for an improved estimation. With this motivation, we propose RP-VIO, a monocular VIO system that uses only planar features and their induced planar homographies during both initialization and sliding window estimation for improved robustness and accuracy in dynamic environments. To implement our system, we build upon WinSmono. We modify its front-end initialization and inference modules to use only planar features and their induced constraints. In the front-end module, we detect and track KLT point features across image frames that only belong to the planar regions. These planar regions are segmented using an off-the-shelf plane segmentation model like Plane Recover, whose plane segmentation masks are further refined using a dense CRF model. Any outlier features arising from inaccurate tracking or segmentation are pruned using a homography-based ransack scheme. To initialize the state of our visual inertial system, we apply a plane-based structure from motion over an initial window of image frames to obtain up-to-scale camera poses and 3D point locations. Since we use planar points, we rely on a planar homography matrix model for the initialization instead of a fundamental matrix model. To briefly review the planar homography matrix, consider the following figure. It consists of two cameras at C0 and C1 observing a point P belonging to a plane. The plane is defined by the plane normal N0 and plane distance D0. The planar homography matrix is a 3x3 matrix consisting of the relative rotation and translation of the two views and the plane parameters. It maps the image observation of the point P from the first view to the second view and can be estimated with DLT using 4-point correspondences. This estimated homography matrix can then be decomposed to recover back the rotation, translation which is in the scale of the plane distance d0 and plane normal n0. Any ambiguity in the decomposition can be resolved using the pre-integrated IMU rotation. To the initialization optimization, in addition to the standard 3D 2D reprojection residual, we include the following 2D 2D reprojection residual arising from the planar homography. After this optimization, the optimized camera pose estimates are aligned with the pre-integrated IME measurements to solve for the remaining unknowns in the scale D, gravity vector, velocities, and IME biases that are required to initialize the visual inertial system. The core of RP-VIO is a sliding window optimization that optimizes over a sliding window of the most recent frames and their measurements. This optimization is a visual inertial bundle adjustment that minimizes the sum of the prior residual arising from the marginalization, the IMU residual, the 3D 2D reprojection residual, and an additional 2D 2D planar homography residual which we include. To evaluate the performance of a system, we use sequences from three diverse datasets. The first is a sequence from the OpenLoris dataset that was captured in a supermarket from a cleaning round robot. The second is a sequence from AD-VIO that was captured in an underground metro station from an iPhone 6s. The third is a sequence from the VIO dataset that was captured in an outdoor simulated city environment. While we used the ground truth road segmentation masks that were available for the VIO sequence, for the two real-world sequences, we used plane segmentation masks from an off-the-shelf plane segmentation model with little tuning. These are the quantitative results. We show an improvement in ATE of up to 40% over Vince Mono. Here we show some qualitative results on the OpenLoris and AD-VIO sequences. These three sequences, though they contain dynamic objects, have a few limitations. Dynamic objects are not present in all parts of the sequence. In all three sequences, especially during the initialization phase, which is often the most fragile part of the system, sufficient IME excitation is not provided, which affects the scale observability and hence accuracy. This is especially the case in OpenLoris, which uses a ground robot. Lastly, the ground truth trajectories in the real sequences are not very accurate, especially in AD-VIO where the accuracy is in the decimeter range. These limitations prevent a thorough evaluation of the effect of dynamic objects on VIO algorithms. For these reasons, we build our own highly dynamic visual-inertial dataset using AirSim. We create 6 sequences with progressively increasing number of dynamic objects from none to up to 8 that are otherwise identical. We also ensure the dynamic characters are present throughout the sequences and there is sufficient IME excitation. This allows the effect of the dynamic objects and the accuracy to be isolated. Here we provide quantitative results of two versions of RP-VIO, one using a single plane and another using multiple planes on our dataset. We compare against Vince Mono and a version of Vince Mono called Mask Vince that simply masks out the dynamic objects. We show a significant improvement in robustness over Vince Mono as it fails to track in 3 sequences, and an improvement in accuracy over Mask Vince owing to the plane-based optimization. Here we show some qualitative results of our system in comparison with Vince Mono on our dataset. We see that Vince Mono fails to track in the C4 sequence, while ours continues to track robustly in all the sequences. Please visit our project page for more details, code, and dataset. Thank you for listening.